Suni. Suni. Suni's training for a 5-kilometer race. She starts out her training run by moving at a constant pace for 4.3 meters per second for 19 minutes. Then she accelerates at a constant rate until she crosses the finish line 9.4 seconds later. What's her acceleration during the last portion of training? What I say the first thing to do was always do a what? Let's draw a picture. Okay? Let's put Suni over here. Suni. Okay? Oh, that's a stupid drawing. What do you think of my running form there? Hmm? How's that? Yeah. Let me fix that. Nobody runs like that. Terrible form. There we go. How's that? Okay. All right. So she's gonna run until she gets to like this point somewhere, and then at that point she's gonna really start running and kicking it into high gear, right? All right. So let's draw like a body lean on here. We got the blonde hair waving in the wind. Okay. Mm-hmm. Yep. Look at that. Okay. Oh, yep. Yep. Okay. We got serious body lean right there. Bam. Really kicks it into high gear there. Oh, thank you. Okay, and then and then at the finish line, what does she do? Okay, she just falls over here. Just there you go. She's at the finish line. Okay. Yep. Mm-hmm. Draw the picture, James. I'm drawing a picture. You draw a picture. We draw a picture together. Greenie, draw the picture. You did? Let me see. Let me see your picture, Greenie. No, did you draw actual runners? You need to draw actual runners. Okay, how long is this whole race? 5 kilometers. So this whole thing is 5.0 kilometers, right? But how many meters is that? 5,000 meters. How long did it take to get from this beginning to the point where she really starts to kick it in high gear? How long did that take? Okay, 19 minutes. So you're saying the change in time here was 19 minutes? Well, shouldn't it be in seconds? Because we normally work in meters per second, right? How are we going to convert it to seconds? So 19 minutes times 60 seconds, right? So 100, it's 1140 seconds. Okay. Did she accelerate this, or was she at constant velocity here? Okay, so her initial velocity was 4.3 meters per second all the way until she got to here. Okay. And then she kicked it into high gear for 19.4 seconds from here to here. So the change in time here was 19.4 seconds. Now, what do we have to solve here, James? What's her acceleration during the last portion of the run? We need to find the acceleration, right? Question mark. But in order to find that, Christian, we need to know, well, if she dies here at the end, what is their final velocity? Well, put VF equals 0. Okay, right here where she begins to kick it into high gear, what's her initial velocity? Yeah, 4.3 right here is her initial velocity. Okay. So is there an equation among the ones we've selected on the board where we can find the acceleration right here? Where? Hmm. Boy, I don't know. Okay. Don't we need to know? Well, okay. The thing is, here's the problem here, Christian. Here's the problem. We have two different times. For this portion, we have 1140 seconds. In this portion, we have 19.4 seconds. So we can't go over here and use this top one because these two times have to be the same. They're not the same. In other words, we can't just put 1140 right there and then 19.4 here. That's not how the equation works. So we can use the bottom one, but what don't we know here? We don't know how far that is. We do know, you're right, we do know that she falls down dead, so that's 0. Her initial velocity, but what we don't know, we're trying to find A, correct? We don't know change in D for the last part, but can we find it? Yes, but okay. We know the whole thing's 5,000 meters, right? If we find that, can we find that? Yes, we can. In order to find that, we probably need to know this part. Okay? So let's label this some letters here. We have A and we have point B. So the distance from A to B, we can find that. How can we find that? Chase, you got any ideas? Which one of those equations on the board there should we use? Just for this part from where she's running to where she's kicking it into gear. You mean the delta D equals VI, the displacement one? You are correct, sir. You certainly are correct. So now, does she accelerate at all, Indigo, during this first part? She does not accelerate. So we should probably write down some info. We should probably write down acceleration equals 0, right? Yeah? So here we go. Let's use this equation right here with the displacement. All right. For this part only, right here. Change in displacement equals our initial velocity times this time, 1140 seconds, plus 1/2 the acceleration during this time times this time squared. Well, what was her acceleration from here to the blonde hair? 0. So does this part get scratched out as 0? It does. No, Greenie, you don't like that? She didn't accelerate, man. She kept the same pace. Okay, same pace. So now look, all I have to do is do what? You were saying that the whole time? Okay, 4.3 meters per second times your change in time, which is 1140 seconds. All right. So what was her displacement just for this part before she turned blonde? You guys got 4902? Yes, sir. Okay. So this is 4902 meters. Now, can we find out how far this part is? 98 meters. You with me so far, Riley? Yes? Okay. So, no, just 98, because how'd you get that? 5,000 minus 4902 is 98. So, Greenie, she got an initial velocity. She falls down dead at the end. It all took 19.4 seconds. The displacement was 98 meters. We got to find the acceleration. Which equation should we use here? The top one? Which one, Indigo? The bottom one. Okay? So, final velocity squared equals my initial velocity squared plus 2 times A times my displacement for this part. Okay, Greenie, what do we know? The initial velocity is, the final velocity is, so we cross that out, we put 0. So 0 equals 4.3 meters per second squared plus 2 times A times 98 meters. Solve for A. This was 0, by the way. Solve for A. Is it okay if you get a negative number for acceleration? Yes, it is. Why? Because she did what? Well, yeah. Okay, what'd you guys get? Indigo, what'd you get? Chris Perrin, what'd you get? What'd you get, Greenie? Allie? No. Did you square this? Did you divide by 2 and 98? 4.3 squared. Why would you want to get A on the other side? Negative, oh gosh, negative 4.3 meters per second. Okay? Square that is equal to 2 times the letter A times 98. Solve for A. Solve for A. So you're going to divide both sides by 2 times 98. What is A? I'm trying to find for A. Why do you want to divide by A? Why do I have to move A over there? Just keep A on the right and solve. It's the same universe. What'd you get, Ryan? Holy crap. 4.3 squared, Greenie. Enter it in. Put it in your TI-83. Year. 0.038. Thank you. 0.09, yes. Mm-hmm. Well, she's running, right? She's running, and she's tired. What do you do when you're tired? Oh, you just keep doing? Or do you go faster, Greenie, or do you slow down? Oh, you go faster? Okay, Greenie. 3 steps past the finish line, you're right. Well, she does kick it into, well, her final velocity is 0, so she actually tries to kick it into high gear, but she ends up slowing down. Yeah. I figure she gets faster. All right, what's she doing in the first part? Oh, well, then it has to be positive then, doesn't it? If she's getting faster, it has to be positive. Yeah. Yeah, that makes sense. It would have to be. Yep. My fault. Miss Rap, I'm going to fix it right now. There. Okay. So, does that make sense what we did? Now, probably confused as to why we just didn't use one equation for the whole thing, right? Right? Well, the reason why we didn't use this equation for the whole thing, okay, was because this time right here and this time right here are different, and you can't put two different times into the same equation. It doesn't work like that. Ryan. Well, the thing is, though, if I started it from point B, I wouldn't know the displacement for this distance here. I got to know the displacement. Well, I used 5,000. I used this equation to find out the displacement here, and so that I could know the displacement here, and then I could find my answer. Well, in both of these right here, you need displacement. Okay, if I don't have displacement of this part in blue, I can't solve anything. Oh, yes, absolutely. Yeah, you could. You'd have to square root the time. But yeah, I don't. Yeah, yeah, you could. Yes. I'm sorry. You would. Never mind. You're right. You're fine. But anyway, yeah. So do you see why we use two different equations here? Questions? Even if you don't know what I did. Christopher, you didn't pay attention to that. You paid attention to about half of it. Did you zone out? What part did you zone out at? So James, you didn't write any of this down? You wrote half of it down. God damn, James.